Okay, today we are going to do a brief history of the periodic table. Um, Here's our therapeutic portion for this, is that although these two guys have been mentioned, Dobereiner was the first one to come up with triads, and Newlands came up with octaves. I've never seen him show up, and I'm not going to ask you about him on the test. So if you want your therapeutic, I don't have to know this, go ahead and cross off this slide. I just had printed him off first. So. Okay, the first guy that we need to be familiar with, and we learned about him last year with the periodic table, is Mendeleev or Mendeleev, depending on your pronunciation. What Mendeleev did is he um, literally put all of the information about elements on cards. He was a solitaire player, and he arranged them into these patterns. And ultimately, he figured out that if you arrange them by atomic mass, which they had the ability to do by the time Mendeleev came around, you found that certain properties showed up at certain intervals. And he published his first periodic table in 1869. Now, the big thing that convinced people is that he left empty spaces and predicted where undiscovered elements should be. And this was a big deal. It's, when these predictions were confirmed, people really bought into the idea and believed that he actually really knew what he was talking about. And that was the big thing that persuaded other chemists, because at the time, with little evidence, a lot of people disagreed with him. Now, there was one other person. Meyer also created a very similar table to Mendeleev's, but the biggest difference is he did not make the same predictions that Mendeleev did. Okay, so because Mendeleev had the predictions, he was in of the new elements that were discovered. Now, the next guy that's important is 1911. Henry Moseley updated it and said the pattern actually worked best if you arranged it by the number of protons or the atomic number. If you remember correctly, if you look at the periodic table closely enough, there are a few opposites where a heavier element or an element with a larger average atomic mass comes first, but the number of protons is what we use now. And that's mostly because Rutherford had finally discovered the nucleus in 1911. So once we discovered the nucleus, once we discovered protons, Moseley just kind of rearranged it. All right, now the next big thing, and some of the other updates to the periodic table since then were really as new electrons were discovered, because the noble gases were added after Ramsay discovered most of the noble gases, and then obviously as we have created new elements. But the basic breakdown, which I think most of us are familiar with, we got the noble gases, we've got the halogens in this column. Our alkaline metals are our group 1s, alkaline earth metals are our group 2s, our transition metals, we've got our lanthanides, our actinides, and then we also have our breakdown to go way back of our metals on the left, our metalloids in the middle, and our nonmetals on the right. So some of these boxes are a little different than what we had last year, but this is the basic breakdown. Okay, we got to talk about periodic trends or patterns. Now, electronegativity is defined as a measure of how strongly an atom attracts electrons when it is in a compound. So I always refer to this as the electron tug of war. Who's going to win, right? And again, this applies when an atom is in a compound, not when it's by itself. And obviously, if we're talking about sharing, a lot of times we talk about covalent bonds, but not necessarily exactly all the time. Now, fluorine is the most electronegative element. It always wins the tug of war. They have designated fluorine as being a value of 4.0, and then we do all of the comparisons for the other ones. This chart's a little tough to see. There's one in your textbook, because I want to say there are some questions in the book where you need these electronegativity values. They're going to come back into play next unit as well, because this is how we're going to determine what type of bond things fall into from a mathematical perspective. Now you'll notice that the noble gases aren't on here, but that's mostly because they don't ever share their electrons. So we go with fluorine. It's going to decrease as you get further away. And the three biggies when it comes to electronegativity are nitrogen, oxygen, and fluorine. Fluorine's the heavy hitter, and then we jump all the way to 3.5 for oxygen, 3.0 for nitrogen, and chlorine too. But the way that for the sharing that these three do, these are usually treated as the most electronegative elements. And this is going to come into play a little bit later when we talk about hydrogen bonding, because these guys are so attracted to electrons. All right, let's see. This is just a visual. Again, here's fluorine with the highest, and then everything's going to decrease. And you'll notice there are some exceptions in here, meaning that we would expect it to keep going down if it followed the pattern, but we've got some dips, and we'll talk about what some of those exceptions look like. Remember, on the trends for the periodic table, this is just showing it would increase as you go this way, and it would decrease as you go down the periodic table. And remember, this is going to be a pattern that a lot of them are going to follow. Okay, the next trend we need to know about is ionization energy. Ionization energy is defined as the energy required to remove one electron from a gaseous neutral atom. Ionization just being the process of forming an ion. The generic form for that, and A, which is here's our neutral atom, it's in the gaseous state. It requires the input of energy, so this is going to be endothermic. All right, it's positive change, so endothermic, and it's going to give us a positive ion plus the electron. And measurements of this are made in individual atoms in the gas phase to avoid interactions with nearby atoms, because if we have something in the gas phase, with kinetic molecular theory, we talk about the fact that there really aren't any attractions between them. Okay, now, a couple of things with ionization energy to kind of take this to the next level. This is representative of what's called the first ionization energy. And all that means is how much energy does it take to remove the first electron. Obviously, your big, major, highest values here, helium is really not going to want to give it away. Neon doesn't want to give it away either. So our highest values are over here. Our smallest values are over here. Really, lithium and sodium and potassium, they want to give their electrons away. So it's not going to take much energy. Okay, so again, these are just some numeric values. And I'll explain. Don't show this message. Okay. I'll explain why there's a little bit of a dip here when we get into the halogens, but I'm sorry, into the nonmetals, but that's mostly the pattern that it follows. Okay, again, this is just kind of showing that on a graph in the fact that all of our group 1s for each of their periods in the periodic table have the lowest ionization energy. And if we look here, this is the second period. You have lithium, we go up to beryllium, we come back down to boron, and that's really just from the fact that beryllium is going to fill the S block, and then boron is going to have one extra in the P block, and it's not going to take as much energy to give that one away. We get carbon, we get oxygen, we get nitrogen, we get a little bit of a dip with oxygen, I'll explain that, fluorine, and then that the noble gases have the highest ionization energy. All right, now the other thing that happens is that if one electron is removed, the positive charge binds the electrons more tightly. So the second ionization energy must be higher than the first. The largest jump in energy is when you then try to remove a core electron instead of a valence electron. So if we look at these, this line separates a huge major jump, and this is when you form those cores. So for example, for sodium, it's pretty willing to give up that first electron. Only takes 495. This is kilojoules per mole. But as soon as you rip that one away, look at the jump here. In order to take that second electron, when you get into the core, all of a sudden it jumps to 4,560. Same thing, magnesium. And if you think about this from an element standpoint, let's see if I can get the pen to work here. Sodium forms a 1+, so that's the biggest jump. Magnesium forms a 2+. As soon as get past that one, it's the big jump. Aluminum is a 3+. Silicon has 4 valence electrons, so that's where you get the big jump here, and then that follows that pattern, and the argons and the chlorines, they start high and they stay high, so that's kind of what we're going for on that one. Let's see, ionization energy, again, across the period, and this is the reason why, is that it requires more energy to remove an electron, so it increases, and the reason why is because the electrons added in the same energy level do not shield electrons from what's called the nuclear charge. When we talk about the examples why we're really talking about the interactions between the positive nucleus and the negative electrons. And so if they're added at the same level, they're not any further apart. Now when we go down the group, it requires less energy, and this is because the valence electrons are further away from the protons that are sucking them in the nucleus. So as that radius goes up and we get further away, that distance is greater, so the attraction is not as strong. And even for the shielding the nuclear charge, the other way I think about it is if you take an electron off in the same level and that one goes away, then it just pulls everything in that much closer. So, okay, so again, here's just a general pattern for ionization energy. Ionization energy. All right, then we get to electron affinity. Now, electron affinity is a little bit kind of like the opposite of ionization energy, in that this is the energy change when an electron is added. And I remember this because added starts with an A. It's exothermic this time because ionization energy was endothermic. And so you're going to have neutral atom plus an electron, we get the anion, and we're releasing energy, so therefore it's going to be exothermic. Now with electron affinity, it has a very similar pattern, except we have to deal with negative numbers. Since it's releasing energy across the period, it's going to get larger, but we're going to say it gets more negative, which I know breaks the rules of math, but the value is going up. And the reason why is because the electrons added in the same energy level do not shield electrons from the nuclear charge. I'll try to show you some animations on this to make this, watch this make a little more sense. Now as we go down the group, it releases less energy, so the number decreases or gets less negative, and this is because again the electrons being added are further away from the proton, so it's going to have less of an impact on that electron. In this part I'll try to explain a little more. Here's our same trend that we've seen really for all of them to this point, that same big giant arrow as we go up across. And then we get to the last two, which are atomic radii, that are going to be a little bit different, and ionic radii falls into the same pattern. Atomic radii can be defined by the edge of its orbital, but since that's fuzzy, the better definition here is half the distance between the nuclei of identical atoms that are bonded together. So if we take this distance of two bonded together bromines, we cut it in half, and then we get our answer. And radii is just plural for radius. Okay, across the period, atoms get smaller because of the increased number of protons attracting the electrons. So as we go from left to right, the electrons being added are in the same shell or the same distance away. So as we add those protons in the middle, they're pulling all of the electrons in a little closer. So the electrons added in the same energy level, again, don't shield from the nuclear charge. Now as we go down the group, the atoms get larger, and that's simply because the energy levels being added to the atom are just further away. And if they're further away, then it's going to increase the size. So here's just again a visual demonstration of that, where you got helium, which is the tiniest of them, neutral atom wise, and then we get increase as we go down, and decrease as we go both down the chart and back. Okay, this is just another picture of that, just showing you, and this really isn't to scale, but just the patterns of the trends. And the atomic ionic radii are going to be the opposite from everything else. So we're going to increase as we go down, decrease as we go across, which is the opposite from everything. Okay, I hope that helped.